My name is Harender Pratap Singh, Assistant Professor from Computer Science and Engineering Department at Rajkumar Goyal Institute of Technology, Ghaziabad. Today I am going to explain the topic of deadlock with deadlock prevention and deadlock avoidance strategies. Right? What is deadlock? Deadlock is the situation in which two or more than two processes are waiting for some resources and at the same time they are holding some resources. That means process are waiting for those resources which are already allotted to some other process. Let's see an example here to explain it in better understanding. There are two processes P1 and P2. Take process P1. P1 is requesting for the resource R2 and same time it is allocated process R1. R1 is allocated to the process P1. Now process P2 requesting, waiting for resources R1 which is already allocated to the process P1. Right? In this way there is a deadlock. Why there is a deadlock? Because there is a cycle in this graph. See here, if I take process P1 is requesting the resource R2, right? At the same time process is holding the resource R1. That means a process is waiting for a resource R2 which is already captured by the process P2. That means process P1 is waiting for the process P2 and process P2 is waiting for the process P1. There is a cycle in this graph and it is in this direction and there is a deadlock. So the deadlock concept says that two processes requesting some resources, that resources is already allocated to some other process. That means process 1 is waiting for process 2 and process 2 is waiting for process 1. So there is a deadlock. Next. So the condition of deadlock. So these are the four pillars of deadlock which state that if all the four conditions in a system occur simultaneously, then we can say system has deadlock. So what are the four conditions? Let's explain here. Mutual exclusion. Mutual exclusion says that two processes want the resources and resources cannot be shared among the process. That means a single resources cannot be shared among the two processes. That is the condition of mutual exclusion. That means if we have one resources and if we want to share that resources between the two processes P1 and P2, we cannot share them. Second condition is hold and wait. That state that one process is holding some resources and waiting for some other resources which is already allocated to some other process. That is the meaning of hold and wait. Third is the no preemption. That state that no preemption says that if a process want some resources or request for some resources, let R1 or R2, and those resources is already occupied by another process, let's say P2, then if the process is in P2 is in state of running, then we cannot preempt out those resources from the running state process. In short, as a summary you can understand like this: if a running process is holding some resources, then it cannot be preempted from the running process. Those resources cannot be preempted out from running process. Now circular wait. What is the meaning of circular wait? Circular wait state that process P1 is waiting for P0 is waiting for P1 and P1 is waiting for P2 and P2 is waiting for P3 and so on. Pn minus 1 is waiting for Pn and Pn is waiting for P naught. There is a circular wait. Process P naught is waiting for some resources, let's say R naught, which is already occupied by process P1, and process P1 is waiting for some resources, let's say R1, which is already occupied by process P2. So there is a circular wait, and if this condition occur in a system, then we can say there is a circular wait. Next. So in this diagram, it is very clear to all of you that P1 is a process which is holding the resource R. Another process is P, which is requesting for some resources R. So this is the resource allocation graph. Next slide. Process are denoted with the help of circle, and resources are in a square box. This is the multiple resource type. Now a process Pi is requesting, arrow is toward the resource requesting, and this is resources are allocated to Pi. This is allocated holding. Next. See, in this resource allocation graph, as I have told you earlier, process P1 is waiting for resources R2, which is holded by process P2, and process P2 is waiting for the resources R1, which is already held by process P1. So there is a deadlock in this graph. See, in this graph, there are the three process P1, P2, P3. R1 is holded by the process P1 and R2 is holded by the process P2. There is no cycle in this resource allocation graph, so there is no deadlock in this graph. Now in the case of multiple instance type, what it happen? See, take the scenario here. Again there are three process P1, P2, P3. Process P1 is holding a resource R1. At the same time, process P1 is requesting for the resource R2. But resources are of multiple instance type. Even though there is cycle, but here may or may not be deadlock. Why? Because resources are of multiple type. Let's suppose A and B, two types of resources are there. So in this case, we have to use separate algorithm that is known as Banker's deadlock detection algorithm. So there in this graph there may or may not be deadlock. Next. Deadlock handling strategy, deadlock prevention, deadlock avoidance. See, what is till now concept is clear. What is deadlock? So as a basic example, let's take a specific example, real life example. If a traffic light signal fail, then all vehicles are jammed, and in that case there may be deadlock. So that is the example of deadlock. Another, take a general example. Let's suppose customer want to open an account. Customer went to the bank, so he fill up the form. There he submit the application form to the clerk. With a clerk examine the form and examine the ID Aadhaar card. If the Aadhaar card address mismatch with the application form address, then clerk told the customer that your account cannot be opened. Because why? Because there is a mismatch of address between the Aadhaar card and the account opening application form. Then clerk tell to the customer that please go to the Aadhaar card center for updating your Aadhaar card. In that case, customer went to the Aadhaar card center, tell his problem. Now what happened? Aadhaar card center agent asked the customer for bank account opening slip. Now he does not have. There is also a deadlock. although second ID can be given, but I want to explain the basic general. So that is also an example of deadlock. Next, deadlock prevention. See what deadlock prevention says. Deadlock prevention also guarantee that there cannot be deadlock before implementing at the design phase and at the development phase. It guarantee that there is no deadlock before running time. It guarantee that there is no deadlock. That is the phase of design and implementation phase. It guarantee that there is no deadlock. They are the 4 conditions. If we violate all these 4 conditions, any one of these 4 conditions, then we can say there is no deadlock in the system. Mutual exclusion. Mutual exclusions. What was the mutual exclusion? Mutual exclusion says that resources cannot be shared among the 2 process, right? That was the mutual exclusion. Can we share these resources among the 2 process? No, it is not possible. Take that example. Let's suppose there are 2 user 1 want to print 10 document with the 10 pages, and user 2 want to print document with the 5 pages. So it will be printed in a serial way. First user print out of 10 pages, then second user print out of 5 pages. It cannot be like this. First user 5 pages, then goes to the second user 5 pages, then comes to the first user 5 pages. It is not like that, because resources cannot be shared, and printer is the resources and it is the hardware property, and so hardware properties cannot be shared. So we cannot violate this mutual exclusion. Next, hold and wait. Hold and wait says that if any process is holding some request at the same time waiting for the another request, another resources which is already held by some other process. Let's suppose, take an example. As I have already explained you previously, that there are 2 processes P1, P2 at the same time requesting for resources R1, and this R1 is already allocated to process P2, and P2 is requesting for the resources R2, and this R2 is already allocated to the process P1. This is of single instance, okay? Right? In this case, process P1 is holding a request, that is R2. At the same time, requesting resource R1. Process P2 is holding some request R1, and at the same time waiting for request R2. So there is cycle, there is deadlock. But how can we violate this condition? This condition can be violated in 3 approach. First approach says that allocate all the resources to the process at the beginning before execution. If we allocate all those resources to the process at the beginning, then in that case we can violate this condition, that is the hold and wait, right? Second approach says that if any process is currently executing, that means running, then holding some resources and want to make some fresh request. That means if a process is holding some resources and want to make some other resources which is already held by some other process, in that case that process has to release all holding resources. That is the second condition. Third approach was process can hold the resource for a finite interval of time. Means any process if holding a resources for a finite interval of time it can hold, then forcefully that resources is printed out from that particular process. That is the meaning of hold and wait violation condition. Next slide. No preemption. No preemption says that if a process is in running state and holding some resources that means another higher priority process cannot primed out those resources from that running process. Resources can be primed out only from the waiting process. If a high priority process such as kernel process, system process can forcefully print out the resources from a waiting process, that is the meaning of this no preemption violation. That means a kernel process can easily print out the resources from a waiting process only, but resources cannot be printed out from a running state process. Next slide. Circular wait. Circular wait violation. Circular wait was, as I have told you previously, process P1 is waiting for, process P0 is waiting for P1, P1 is waiting for P2, and Pn minus 1 was waiting for Pn, and Pn was waiting for P0. There was circular condition as we have told earlier. But here, how to violate this condition? There are three approaches to violate this condition. First approach says that let's suppose there is a process P1 and they are the resources R0, R1, R2, R3 and so on Rn. A unique number is given to all resources. Now the process can request all the resources in the increasing order like this, either in the increasing order or either in the decreasing order. That is the meaning of, in this case we can easily violate circular wait. If a process requests in the increasing order, then the process cannot go back for any resource. That means if a process cannot go back for any resource, then there is no cycle. Cycle only occur when a process is requesting a resource and has to go back, then there is a cycle. As we have previously discussed this, either in the increasing order all the resources are allocated or either in the decreasing order. In that case the process can easily violate this circular wait condition. Second approach, if any process is holding a higher resource number request and request for a lower request number, yes, same example. Take here P1 process, resources R1, R2 and so on Rn. Let's suppose this is already given, R2 is also given, right? This resources is already holded by this process R1, R2 and R3. Now R5 is also given. Now here a new resource, that is R4, requesting, this process is requesting for the resources, arrow is toward this requesting. In that case already it is holding the resources R1, R2, R3 and R5 and now want to a fresh request of R4. Now in that case this resource can be allocated only if this process release all the resources above this number. That means the process has to release this resource, then only this R4 will be allocated to the process P1. That is the meaning of this violation of hold and wait. If any process request for a resources which is smaller number, then it has to release all the higher number resources. If any order of execution are same, then only one process will be executed with all resources, like this. Let's suppose two process P1, P2, right? the order of execution is R1, R2, here R2, R1. Now the order of execution of this process, first R1 is allocated to this requesting for R2, for P2, R2 is allocated to the P2 and requesting for R1. If we change the order, that means P1, P2, R1, R2, make the order same, R1, R2. Now among this and any one of the process will hold the request R1. Let's suppose P2 hold the request R1. This request is given to this particular process R1. Now the P1 is not in competition. Why? Because it says that if any resources is given to any process, then the other will not go for R2 because it is not holding R1. The process P2 is holding R1, then it will go for R2. Then this process is not in competition. Only one process P2 is in competition and it will execute all the resources. Next slide. So disadvantage of deadlock prevention. There are two disadvantages: low device utilization and reduced system throughput. What is throughput? Throughput is the number of tasks which are executed per unit interval of time. That is known as throughput. These are the two disadvantages of deadlock prevention. Next slide. Deadlock avoidance. Deadlock avoidance is also a strategy or a method in which deadlock is permanently removed, or deadlock is permanently removed from a system. How it is removed? It says that at the run time, all the process demand, let's suppose process P1, P2, all the process need demands for resources. P0, P1, P2, maximum demand. Three types of resources are there, 3, 4, 5. It says that P0 want A type resources 3, B type 4, C type 5. That is the maximum demand of process. Same P1 can also have, P2 can have its own maximum demand. So safe state is a state in which there is no deadlock and the process request for its maximum demand, as we had discussed in the previous example. What is an unsafe state? A unsafe state is a state in which there is a deadlock and the system is not able to fulfill the demand of process. That means the resources which the process need are not fulfilled by the system. That is the unsafe. Next slide. So here in this diagram, deadlock, if there is a deadlock, then there is unsafe state. So process is not able to execute its resources, and in the safe state there is no deadlock, there is a safe sequence. Next slide. So in a single instance, if there is a cycle, then there is a deadlock, but in a multiple instance type, if there is cycle, then there may or may not be deadlock. We have discussed this in the previous slide. Next slide. Banker's algorithm. So Banker's algorithm is the deadlock avoidance strategy, which says that we have to adopt the safety algorithm in this Banker algorithm because it used to provide the safe sequence. How? Next slide please. See, available, max, allocation, need, finish. What is available? Available means the number of resources which is available at that particular time for allocation to a particular process, and max is the maximum number of demand a process can request to the system. That is the max. Allocation means maximum allocation means the at a particular interval of time when the process is going to execute, then the available resources which is given to the process for execution, that is the allocation. And what is need? Need is always calculated as max minus allocation. That is need means for the execution of a particular process, how much need is required by that particular process for execution. Finally finish. Next. So how to implement this safety algorithm? See, first we allocate the available to the work. Always initialize the available to the work, and now for each I equal to 0, I equal to 1, we find out that for a process need P naught is less than equal to work. If it is true, then in that case we have to update the work equal to work plus allocation. In this way we check all the process and find out the safe state of a system, and if there is a safe state of a system, then we can say there is no deadlock. How? With a basic example we can discuss it here. Next slide. See, in this Banker's algorithm there are 4 processes: P0, P1, P2, P3, P4, right? Allocation means this resource, yani ki you can say that P3 resource type A2 is allocated, resource type 1 is allocated, C type 1 is allocated to this P3, right? For allocation, for execution, this types resources are given to this particular process. So all of this you can easily understand, these resources are already allocated to this particular process P0, P1, P2, P3, P4. Now what is max? We have discussed it previously. The maximum demand of the process before execution, that was the max. So maximum, how to read it? P0 need maximum resource A type 7, maximum resource B type 5, maximum resource C type 2. That means for execution it can need 7, 5, 2, right? Now available at a particular time, A, B, C type resources available was 3, 3, 2 at a particular time, right? Check the condition. Need is less than equal to work. First we check out for P0. So what is the need of P0? Need is calculated as max minus allocation. Max is given here, allocation is given here. 7 minus 0, 7, 5 minus 1, 4, and 2 minus 0, 2. Like this way we calculate out the need of each process in a system. Now check the condition. Need is less than equal to work. So what is the need of P0? Need is here. 742 is less than equal to work. Work is what? We have already told that available is equal to work. So what is work here? 332. Condition is true or false? Condition is false. Need is not equal to work. Less than not equal to work. So this condition false. So P0 has to wait. P0 has to wait. Come to the second process, P1. So what is the need of P1? 1, 2, 2. Less than equal to available. What is available here? 3, 3, 2. Condition is true. And if the condition is true, then update the work equal to work plus allocation. So what is work? 3, 3, 2. What is allocation of P0? P1, sorry. What is allocation of P1? Allocation of P1 is 200. Add this 532. Now come to the process P3. I equal to 2 here. Process P2. Now check for P2. Need of P2 is 600. Less than equal to available. So what is available here? Updated work here 532. This condition is false. 600 is less than equal to 532. This condition is false. So again P0 has to wait. For a weighted process, I am using the notation double circle. So here also was one weighted process as P0. So double circles is the notation for a weighted process. So this process was executed, right? Now come to the P3. What is P3? Need of P3 is 011. Sorry, need of P3 is here 1. Need of P3 is 011. Now put here 011 is less than equal to 532. 532. Condition is true, and in this case work will be updated as work plus allocation of P3. Allocation of P3 is 2 1 1. In this case updated work. This also execute. P4, need of P4 is 431 is less than equal to available. Available is what? 743. Condition is true. Condition is true, then we will update the work. 743 plus 002. What is 002? Allocation of P4. We are checking P4, right? This also executed. Now then for waiting process P0. Now P0, how? P0 will check what is the need of P0. Need of P0 is 742. 742 is less than equal to work. What is work? 745. Work is 745. Condition true, and this condition is true. Now again we have to update the work. Work equal to work plus allocation. What was the allocation of P0? 010. 010. Now it is added. It became this. This is also executed. And P0 is also executed and P4 is also executed. Now P2 600 is the need of P2. 600 is the need of P2, and need is less than equal to available. Available here became 755. This also true, and work is updated as 755 plus 302 1057. See, when we add this total 2 plus 3 5, 5 plus 2 7. Here 1 plus 1 2, B type. C type how much? 2 plus 1 3, 3 plus 2 5. This was the allocation. A type 7, B type 2 and C type 5. If we add this allocation with this available which was given in the question, that means 7 plus 3 10. Total A type resources which a system is holding 10. 2 plus 3 5. Total B type resources which a system is holding, that is 5. 5 plus 2. Total C type resources which a system is holding is 7. And in this result we also get 10 5 7 at the last. So this is matched with this figure. So this sequence is the safe sequence, that is P1, P3, P4, P0 and P2. If we execute this, if we execute in this order, then we can say that the system is in safe state without deadlock. That's all for today. Thank you. Have a nice day.